Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. What we are discussing was miscible displacement. In particular, we are talking about mixing that takes place as flow occurs inside a porous medium. So, what we discussed before is basically we are talking about dispersion of solute or tracer in porous media, and we have first looked into how it occurs in a capillary, and then came up with concepts called dispersion coefficient, which involves both diffusive component as well as the effect of velocity, because mixing is contributed both by the tendency of molecules to break free and move into other territories. So, that is one thing. Second thing is this is also enhanced by the flow that takes place, because mixing is also a function of that. So, we came up with a concept called dispersion coefficient for a capillary, and then we tried to extend that to porous media. So, now what we were discussing at the end of last lecture was the dispersion coefficient in a porous medium. So, here now we are going to discuss about two different types of dispersion coefficients, because this would be important. So far we have been talking about only unidirectional flow, but once you have an infinite porous medium on this, then there would be a longitudinal dispersion, and there would be something called a transverse dispersion. Longitudinal means that the flow is taking place in this direction. So, in this direction there would be a dispersion happening. We have talked about tailored dispersion, these are all longitudinal dispersion, but at the same time there could be another spreading occurs that occurs in the transverse direction as well. So, what researchers they have done, what the academicians they have done was that they have calculated these dl by dt, and they found that longitudinal dispersion is dominant. Obviously, it varies from 3.66 to 19.8. So, the dispersion in this direction, in the direction of the flow, this dominates, but there would be some amount of spreading also in the transverse direction. Now, in many cases this transverse direction dispersion is not considered, because the application may require only considering the longitudinal dispersion. In this context, there is a term which is defined, which is called dispersivity. Dispersivity is, I mean, in porous media literature, porous media related software, generally they ask for what is the dispersivity we should consider. So, dispersivity is essentially, this is defined as AL, which is this longitudinal dispersion divided by interstitial velocity. So, so a lot of times in softwares you may be asked to feed in this data, what is the dispersivity. So, dispersivity is nothing but longitudinal dispersion divided by the interstitial velocity, and dl by d, this itself is a function of Peclet number, and Peclet number we all know is the interstitial velocity average particle diameter divided by d. We said that this is basically the convective divided by diffusive contribution, convective contribution to mixing divided by diffusive contribution. So, that is why in the numerator we have this interstitial velocity, and in the denominator we have the diffusivity term. We have already studied, we have seen that Peclet number, if it is small we go for pure diffusion, whereas if Peclet number is very high we will go for pure convection. So, we are already familiar with this Peclet number. Now, this dl by d, I mean there is a I mean, this is a common trend among among these researchers here, is that there is people tend to plot dl by d as a function of this Peclet number, and they found that these, I mean, they have picked up different kinds of porous medium. They are different types of particles. They constructed porous medium and they had run it. They had run, and after they did all these, they plotted, they made a log plot, and they generated a curve something like this. Okay, so this dl by d as a function of Peclet number. Generally, at low Peclet number or Peclet number tending to 0, this dl by d, it has some magic number everybody has converged to, which is 0.67, and generally they attribute this whole thing to the fact that when Peclet number is truly small or insignificant, this convective part is not at all present. That means, it is flowing at such a low rate that convection does not have any effect. So, it is completely diffusion, this transport is diffusion controlled. So, if there is a diffusive transport, so any flux, any longitudinal, in longitudinal direction, any movement is basically arising from the diffusion, and so it will follow minus d del c del x type form. And then what they had done is, if somebody divide this bulk diffusivity by a factor known as tortuosity, to account for the fact that here the diffusion is taking place inside porous medium, not in a beaker, not in a it is not a free diffusion. So, I mean, it has to go through all the tortuous pathways, the diffusion pathways are now increased. So, that is why they have put in one tau here, and there is some factor there, some tortuosity factor there, and then some factor which is arising from these arising from this particular situation, that inside porous medium diffusion is not, molecule is not free to move, molecule will be restricted to move in tortuous path. And then further, the concentration, the definition of concentration here, I mean, if you see, you can write it, a concentration we write as kg per meter cube. So, when we write kg per meter cube, that is kg per meter cube of that solution. So, so many say I am writing this is so many kg per meter cube is the concentration, or so many moles per meter cube is the concentration. So, moles per meter cube of the solution, but here this meter cube ideally, I mean, if this meter cube is not, meter cube is solution which is in only in the void part, plus there is a solid volume. So, if you are expressing this concentration as so many moles divided by the porous medium volume, so one has to account for that effect. So, one has to bring in that porosity term. So, that is why one has this ratio. So, this ratio basically contributes to 0.67. So, otherwise it is so this is something which people have already seen. So, there are good amount of literature available, where in porous medium there were studies made and reports made on what is the dl by d for a particular porous medium as a function of Peclet number. Okay. And these they have done for different samples, and they have created sort of a domain, I mean range within which they say, for example, within this window they will behave if the grains are fine grains or coarse grains, depending on that these lines will change and how they will change. So, that kind of studies have been done in this regard. So, this is what I was referring to, that these dl by d, or I mean longitudinal dispersion or transverse dispersion, and then they put these on a log scale. So, log scale, when they put, you can see this value is converging to 0.67, and then these are for these data points. So, all these points, these are for longitudinal dispersion, and they found that this is the line for fine sand and this is the line for coarse sand with porosity 0.34, and all data points, they are within this band. Okay. Similarly, for transverse dispersion in transverse direction, so there also they had created a band. So, this kind of studies have been done, and generally if an unknown sample has to be studied, So, then one has to run the dispersion test. That means, one has to conduct a dispersion experiment and then one has to find out what is the dispersion coefficient. I mean to say that I give a step change, I get these are the points and then I have to fit a line through that, and what should be the value of what we call that time was dCt. So, what should be the value of dCt such that these line fits the experimental data points perfectly. So, these kind of studies have been done systematically for different sets of porous medium, and these are the this is how the observations are summarized. So, this VDF in this context, VDF is the interstitial velocity, dP bar is the particle diameter. So, because porous medium is consisting of particles. So, this particle diameter, what is the average particle diameter, that is dP bar, and this d is the bulk diffusion coefficient. So, this type of exercise has been already done. Next thing what could be of interest in this context is two-dimensional dispersion. So, in two-dimensional dispersion you can see we have been only talking about what we had picked up a differential element. We picked up a differential element and we tried to find out how much is going in by diffusion, how much is leaving from the other side by diffusion, how much is going with the flow from this side, how much is leaving with the flow from other side. So, that difference. So, diffusion in minus out, convection the solute which is entering through convection, that in minus out. So, those terms and difference is accumulation. So, that is how we had these. This is the contribution from the diffusion term, this is the contribution from the convection term. VDF is the interstitial velocity. This we have studied in previous lecture. Now, if someone has both longitudinal dispersion and transverse dispersion, that means they have another dispersion component in this direction here. So, that has to be accounted. So, one can put these dt, one can put this contribution of transverse dispersion, and they have included this term as well and calling it a two-dimensional dispersion. So, now once again there are some simplifications possible to this equation. First of all, if one assumes steady state, this term will go to 0, and then this if one neglects longitudinal dispersion, I mean if this needs to be simplified, in the event this longitudinal dispersion can be neglected. When can it be neglected? Convection dominates, diffusion is not dominating. So, in that case one can only focus on convection for the longitudinal part, because that is what is dominating, and then one will left with this form of an equation. So, this part is considered 0, this longitudinal part also goes to 0, and so it is a play between this and this. So, that is what we have written here, is that the convective term, this goes to the other side, is equal to dt del square c del y square. And by now this kind of partial differential equation you have already I mean I have discussed this in one of the earlier lectures. Is I mean 1 or 2 lectures back we had discussed about how to solve this using Laplace transform. This is very similar to what we had there, because that time we were solving del c del t is equal to d del square c del y square. So, instead of this is now the equation. So, how to solve this kind of equation? Generally the solution would be in error function term, and that approach. So, with the right boundary conditions, that approach we have already discussed. So, this is also another way to handle things analytically without complicating, because if you bring in this longitudinal dispersion, there may be analytical solution available, but it is most likely one has to resort to the numerical solution. So, instead of that, still one has the analytical solution for this kind of equation. So, one look for opportunities that if one if this kind of assumption be made, that longitudinal dispersion is neglected, then the treatment would be much simpler and easier. So, this is these are the innuendos one has with regard to this dispersion. What I have next is something little different. Let me talk about this. First of all, when it comes to flow through a fracture, in a porous medium there can be a fracture. If flow through a fracture, it would be something like this, that if this is the well, and from the well there could be a fracture running. That means, we already talked about it, there could be a crack running. Either this, or it could be either this, or it could be that there are multiple small fractures and they got somehow connected. Their fracture can occur due to different reasons. It could be that one has by mistake over pressurized the porous medium, I mean put additional pressure, and so it could not bear, and so there is a crack developing inside. It could be that, or it could be due to thermal stresses. You have heated it and the heating was not uniform, or there is a sudden heating or cooling, and because of that thermal stresses developed, and so because of that it has cracked. So, it could be in a porous medium that one has, I mean one was it could be just a manufactured or processed porous medium, there also the same thing can happen, or it could be even somebody is looking at the subsurface processes, there also the same thing can happen, that in a underground reservoir, because of thermal stresses means one injects water and the reservoir itself was at a higher temperature, one is injecting cold water. So, this thermal stress can cause fractures, I mean because in certain locations it can happen, and there could be other geological reasons, tectonic stresses and other reasons, because of which there could be fractures. And at some point when it comes to reservoirs, there is a possibility that one can resort to something called hydraulic fracturing. I mean intentionally inject some liquid and create a pressure, so that a fracture generates around a well, to leverage few things, I mean which you can in fact very well see that we have already seen when we look at a well, when we look at a cylindrical system, we have talked about this VR, the radial velocity, in earlier lectures. So, there we have seen that the VR is increasing. I mean if we plot mod of VR, that is increasing very rapidly as R decreases. So, that means near the well the velocity has to be, radial velocity has to be very high, whether you injecting or producing. So, that is why I am writing it as mod of VR. So, because of this high velocity, so it is better if one can have some more area for collection of this fluid, because you are collecting the fluid from all over the reservoir and you are collecting it through a small place. But instead of that, if you could expand, if you can create some kind of manifold through which these fluid can be collected or through which the fluid can be injected, then this type of sudden rise of VR at smaller r can be avoided. Okay, and so this can help tremendously with regard to pressure drop, and pressure drop means that is one has to generate this pressure somehow or the other. So, that would simplify the matter very much if one can create a manifold. So, one way of doing it is to create a fracture around the well, so that the fluid can be delivered or fluid can be injected through this. So, it is basically acting as an extended source. We had a point source earlier and VR was drastically increasing. Now, instead of a point source only, now we have a line source attached to it. So, this is so now this is either line source or line sink. So, these are some of the reasons for which one does fracturing, and when one does a fracture, so when the flow takes place through a fracture, what kind of dispersion we can expect. I have already mentioned before that if one has the, I have already discussed before that if one conducts the dispersion experiment in a core that is already fractured, we would be seeing an immediate breakthrough, and then gradually there is a long tailing of the response. So, it was immediate breakthrough, and then there is a long tailing to reach this beyond 0.6 or so, then there is a long tailing to reach that 1.0. So, this type of profile we have already seen when there is a fracture present. Now, when it comes to flow through a fracture, there are two ways we can think of this flow to happen. One is, I mean, when you have a fracture embedded inside a porous matrix, mind it, embedded in porous matrix, there are two kinds of flow that takes place. One is when I am injecting at a very low rate, at a very feeble rate. This could be, for example, I am injecting a contaminant into the fractured porous medium, or I am injecting some tracer. So, these are injected at a very low rate, and the fracture is it is a thin fracture. We are so in such situations, it is probably it is better to consider the flow through the fracture as a unidirectional flow. That means, this is the fracture and this is the adjoining matrix. So, we can expect the flow is happening through the fracture, and then there is some diffusion molecular movement of solute into the adjoining medium. So, this is something which we could think of. So, it is more of an unidirectional flow through the fracture, and then there is some amount of diffusion. On the other hand, so this is for all practical purposes, this is true if somebody is looking at a transport of some contaminant, transport of radionuclide, some transport of transport of tracer, which are done at a very low rate. The pressure here is not much. Of course, the pressure this side is higher than this side. So, there is a flow, but the overall pressure at which this whole scheme is working is at a low pressure. On the other hand, when someone is having a flow through a fracture which is at a very high rate, for example, one is trying to fracture. So, that time they will do it at a high pressure, or when they are producing, they are injecting the fluid which is of value to which is of value. So, these here the objective is to have the highest amount of production. So, there the pressure at which this fracture is held is a much higher pressure. So, in that case, one can think of the fluid flowing from fracture into the matrix. In fact, this is the case where we call this is some kind of a regime. The earlier regime that I mentioned, it is a linear flow regime. That means, flow is taking place linearly in one direction along the fracture. But now we are talking about a regime which is more of a bilinear regime. That means, a flow through the fracture, and perpendicular to this there would be a flow into the matrix. Earlier we considered these to be diffusion, that molecules they will diffuse into the adjoining porous matrix because of their Brownian motion and everything. But now we are talking about a Darcy flow in this direction, because the pressure in the fracture has been jacked up. So, pressure in the fracture is much higher, compared to the adjoining matrix. So, we would expect that there would be a Darcy flow. So, at that time these fracture is acting just as a line source. So, there are two ways to look at these. So, I just wanted to, first of all, I wanted to differentiate these two types of flows. So, that is why I have put this plot here. This shows these kind of two linear flows that are mutually perpendicular to each other. One flow is along the fracture and the other flow is from the fracture into the matrix. So, basically if this is the, we expect that as if so the pressure in the fracture is following this line. So, this line we have already shown here by this line. So, pressure in the fracture has to go down because we have flow through the fracture. So, there is this pressure has to be go down, flow will take place from higher pressure to lower pressure. But at the same time this pressure in the fracture is higher than the pressure in the adjoining matrix. So, if I follow these lines here, this is the pressure profile in the matrix. So, that means these are, so along the in these, so there is pressure is higher, pressure is lower. So, there would be flow from fracture into the matrix, and here also flow from fracture into the matrix. Okay. So, this is what we are referring as so called bilinear flow, one linear flow along the fracture, another linear flow perpendicular to the fracture and into the matrix. And we expect this line not to be straight line, rather this line is carved. This line would have been straight line if there is no loss into the matrix, no fluid going into the matrix. But since any element as any flow that goes here, some part is going in this direction, but some is lost into the matrix. So, naturally, I mean you remember if I had a one dimensional flow through a core, I would have expected the pressure drop to be linear. But here in this case the pressure would not be linear, pressure would be carved because there is continuous loss of fluid into the matrix. So, this is something which is the pressure profile that fracture will follow, and this is the pressure profile which matrix will follow. So, this is something which I have tried to draw here. So, this is the pressure along the fracture and this is the pressure towards the matrix. So, now we need to so what I will briefly do in the next lecture is I will try to quickly show how this type of two linear flows at least can be conceptualized. Okay. And then next we would focus on one I mean only single linear flow which is done for a tracer test, and we will try to find out how dispersion takes place in this in that situation, because when there is fluid flowing from fracture into the matrix, the flow is somewhat different. You can think of here that the flow is going from here to this direction, and also flow is moving in this direction. So, if there is a very little chance for this fluid getting diluted when you are collecting at the outlet, because it is the same fluid which is flowing. So, one can think of, suppose I have this is the fracture. So, moment we introduce a packet of this solute, the packet of solution which has a higher concentration of solute, this packet will be immediately stretched to a straight line. I mean that is what these two linear flows all about. This will be stretched in the form of a straight line, and then this straight line will start growing, this straight line will start growing, this straight line will start growing and go into the matrix. Flow will continuously take place in this direction, but this will also grow. So, when it comes to this fluid that we get from the outlet, once it gets, so I am pushing all the fluid out from fracture into the matrix. So, there is very little chance that these gets diluted, these particular fluid gets diluted compared to the situation when there is not this flow is absent, we are only having one linear flow. So, that is why in this case probably the chance of dispersion is somewhat less. If at all dispersion happens, dispersion will happen here inside this. So, one front is coming and getting into the porous medium. So, one has to now look at this dispersion, which is just a classical dispersion of porous medium. It has nothing to do with fracture. From a line source, fluid is entering and this is undergoing dispersion. One has all those longitudinal dispersion, DCT, etc. So, those will be appearing here. But when it comes to the fracture, we do not have that possibility. On the other hand, when we have a linear flow through the fracture only and no fluid going into the matrix, in that case there is truly a dispersion happening at the outlet end of the fracture. So, these are some this issue I would like to delve into this further in my next lecture. That is all I have for this module. Thank you very much.